In this video, we will do simulations of neural networks to approximate the function. So just like we did in the previous video, let us assume that we have one function y of x1 and x2, and we want to estimate it, and it has two inputs and number of neurons. It can be any number. We will begin with 3 or 4. We can choose it accordingly and then increase the number to see the behavior of our simulations. So to begin with, let's set up the simulation environment firstly. So we know this, that for all simulations there must be some time interval. So let's suppose that our simulation time is 10 seconds. Now after that, let's define the functions. So let me define the function. Let's say our function which we want to estimate is sine x1 plus 0.5 times x2 square, right? X2 square, sorry. Okay, I made a mistake here. This should be x2 square. Okay, now we have two inputs, so let's define inputs x1 and x2. These inputs should be defined before y function, because if we define it after this ninth line, then when the code reaches this ninth line, it will ask for the values of x1 and x2, but it will not exist. That's why we have to define this before the output function. So let's suppose our input function number 1 is sine t, and input number 2 is cos 2 times t. This is same as the previous one. Okay, so this is, I will write comments also. Input, this is also input, and this is output function which we want to approximate, and this is simulation time. Okay, now for input you can see that we have sine of t. So what is t? Actually this is the instant in the interval from 0 seconds to 10 seconds. We can divide this into many instances. Let's suppose we want to do approximation at 0.1 second, then 0.2 second. So we will define t equal to from 0 to 10, but it should have this instance 0.1. First the approximation or the numerical derivations should be performed at 0.1 second, then 0.2. So it will increase from 0, then 0.1, 0.2. Just to make it a little more easy to understand, let me call this dt. So if in future I want to increase this interval or decrease this interval, I can do it directly by simply one command. I simply need to change this. If we want 0.001, so I will simply come here, click over here and change this value. So now, so far we have all the values, and okay. Now I have inputs, I have outputs, I have set up the simulation with simulation time. So let's go and set up our neural network. Neural network setup. So if you recall, we used this n, which was representing number of neurons, right? So number of neurons, and then we had m with a small n, which was two inputs. So this is number of inputs. Number of inputs. Okay, we can see here x1 and x2. So just so we don't get confused, let me rename this to m, and let us assume that we have two neurons, or maybe three. It doesn't matter, because we will not be making a hard-coded program. So we can change this value whenever we want in simulation. We simply have to just click here, change the value, and it will work. After that, now what is the first step? Now let's begin with neural networks. Neural networks, calculations, or whatever you want to name it. After that, what is the first step? If you recall, we had to initialize the input weights. So let's choose some random number. This is a command in MATLAB, m comma n. You can also recall its dimension. It was dependent on number of neurons and number of inputs. And then we had to initialize the output weights as well. So let's choose this as well. And its dimensions were m comma 1. It was a vector, if you recall. This was a vector and this was a matrix of weights associated with input, vector of weights associated with the output. In numerical example, what I did, I chose the bias values as 0. So let's choose its zeros here as well. Okay, this was the bias with input, and b bar, I chose this, let me call it b naught, as 0 because it was a scalar value after the multiplication. Okay, so these are the parameters the network will learn as well. If you remember, we had to update this w and v, and we derived some mathematical equations for it. But at this point, the network has no idea what the correct output is. So we initialized this value and begin with the neural networks. After that, what we needed was the sigma activation for activation, sigma for activation. So we use sigmoid function to, so let me define this a variable of, let's say, z, because this is what we are going to use. It's 1 divided by 1 plus exponential of minus z, right? We use this equation many times. I'm sure you have memorized this. Another key point here is that we had to derive the derivative of this sigmoid function. So it was really easy. We also have a video about this, how to derive it. So let's call this as z, and this was simply sigma z, right, times 1 minus sigma z. Sorry. Okay, so this is the derivative of activation function, and this is activation function. Really easy so far, right? Okay, one question you might be thinking, that why we do this dot multiply by this, because this is the element wise multiplication. If you remember, the dimensions were 2 by 1 for one case, or I think 3 by 1 or 1 by 2 by 1. It was a vector actually, and multiplication was not compatible, so we had to go with this special multiplication, which is actually the element wise multiplication instead of matrix multiplication. So after that, what we need is that we have to set up storage variables. Why do we need storage variables? Because we have to find v hat. Okay, so v hat, we have to make an array of this zeros. You will understand after I write this command, size of t. So if my simulation is performed from 0 to 10 seconds, so this will create a zeros array with a size of t, because here, if you go back, we are doing simulation for each instant such as 0.1. So that's why I wrote size, and its size can be bigger or smaller. And then I initialized it to zeros, because these zeros will be replaced with its real value. Similarly, I have to define this error zeros, because we need this error for computing the gradient descents. Okay, now what is left with us is that when we perform gradient descents, so we will be needing eta. If you remember, we will be tuning parameter. If you remember, there was eta, and we will set it to 0.1 to begin our simulation, and then we will see what happens if I increase or decrease this value. So far we have set up this value to 0.1. This is the learning rate. It controls how fast the network learns. So with setting it to a bigger value will result in different performance, and setting it to a smaller value will result in a different performance or estimation. Now next is, if you saw the video of the iterations for matrices and vector case, so we did 2 iterations, right? Here we will have many iterations. Why? Because simulation time is from 0 to 10 with each instance or interval of 0.1. So what I'm going to do is I'm going to use a for loop, because I have to repeat all these calculations. I cannot write my code if I'm going to use if I'm going to perform 100 iterations, so I cannot write 100 iterations. What I can do is I can use the for loop, and you can see I will use for loop for I is equal to 1 to length of t. So again, length of t, right? And then I will end this code over here. This is a bit better, so we don't get confused with these commands. So let me move this to a bit center. Okay, so why we use for loop? For iterations. Simple answer is for iteration. So at each time step, the network sees one input or number of inputs and updates itself. Now the real work begins. So first thing is to define to define the input vector. We already know this. So x is x1 of I. For example, it will be performed for 0.1 instance, and then x2 of I. Okay, just to explain this command to you, so this is actually a column vector. So if I remove this, this becomes a row matrix. If I add this semicolon, this makes it a vector. So what actually happens here, we bundle the 2 inputs into a vector. So this is why we use vectors. Everything becomes cleaner and more systematic. If I do scalar calculations, it will be a mess here, and I will have to write many equations. You will see once again, after having this input vector, let's do linear combination. So you will see it's really easy. Z equals to W times X plus B. That's it. I don't need to do W11 times X1 plus W12 times X2. If you recall those videos, it was really lengthy. It was easy, but really lengthy. With matrices, it becomes really easy. One thing you can see here that I did not put a dot here because we are in need of a matrix multiplication. So now, what is the next step after linear combination? It is activation. Again, you will see it's really easy. Let me write here, H equal to sigma of Z. We have already defined this function up there. And after that, it's really easy, estimation of Y. So we remember this, we estimated, or we Y hat, we can call it whatever suits us. So we will see, because I need to see this because MATLAB give me this prompt Y hat, because Up there you may see I defined this y hat. So let me define this as a vest. I will tell you why I'm going to do with y hat. Y estimated is really simple. We have initialized this, transpose times h, right? And then plus b naught. So we have all these values. Really easy. We have performed first iteration. But after that, how we are going to do the learning? So for learning, if you recall, we defined the error. So what is error? Error is y real at that instance. For example, 0.1 second, it can be 0.2 for the next iteration and so on. Minus y est. Okay, y estimated. So this is the error. Let me write this like with this comment. Next step is to perform the gradient descents and back propagation and all those derivations, if you recall. So we remember this, we remember the formulas. So let's use that. Gradient descent and back propagations and all that. Let me move this code a little upwards so it can be in the middle. So we remember this dj by dv. This was equal to eh. So I have defined this eh as error here, ERR. So error times h. Really easy, right? We remember this, that dj by dw, this was equal to minus error times q times h transpose. Why q? Because if you remember, we had derived this equation q because it needed a special multiplication which was element wise multiplication. So what I'm going to do is I'm going to define q before this. So q was v times, because vector multiplication, you can see I put a dot here, d sigma of z, right? So this was for the output, this was for the input. We did not derive the derivations for dj by db, but it's really easy. You can derive this like this, minus error times, its process is same because b does not appear directly into the loss function, so we have to use the chain rule and make an equation like that, and we will be able to derive db. So this you can memorize this dj by db and also verify this in your notes. So dj by db is actually error times q, and similarly the output weight, let's say dj b naught, is equal to minus error. Okay, you can define this, it's really easy. So now what's next? I don't know why this is giving us please error parse error at. We will see this. If we have any errors, we will see and solve the errors accordingly. So these lines computes gradient. Each gradient tells us how a parameter should change to reduce the error. Now next step is parameter updates. If you remember, w new is equal to w old minus eta, right? I will write the equation here so you will recall it. So w new was equal to w minus eta times dj by dw, right? And similarly v new equal to v minus eta times dj by db. Similarly, b new is equal to b old minus eta times, this is a standard formula, we just have to divide it. Okay, I know the mistake is I'm using these divisions, so I should not use this because MATLAB reads it as a division. So now you can see when I click here, so it shows me that it is defined over here. So b is equal to b minus eta dj db, okay, and b naught, which is the new one, equal to b old minus eta times. There is one concept I will explain to you shortly why I am not using w new. So what happens in programming is that we already have w, which is we initialized in the beginning, and we already have these values. We have eta, we have dj, dw from here. So in programming, mostly right hand side is computed and then it is given to the left hand side. So instead of writing new here, what will happen is that MATLAB will solve this right hand side and update this value of w. So previously we had some value of w over here that will be replaced by the new value. So I don't need to write w new over here. Similarly for v, b and b naught. Okay, so this is actually gradient descent. Every parameter is nudged in the direction that it reduces the error. And for error we defined that loss function, so our goal was to minimize that loss function. So this is learning in action. I will simulate this and let's see if it works. Then if there is no error, then we will plot the results. So it is busy now. Yeah, it works. So let's see if we have performed the mathematical derivations correctly. So we will plot the results now. Graphical view of results. So let's call it as a figure. Any figure? No. If anyone knows how to close this automatic prompts, please let me know. It's really annoying. Anyways, figure. So let's plot it this way. Let me plot t y underscore real. Hold on, because on the same plot I want to plot t comma y est, which is estimated function. So if I click here, it means I have y estimated here somewhere in the code. When I click here y real, it does not show me, so maybe I have left out something over here. Yeah, so this is y. I can name this as y real, so I can remember it easily. Okay, it's the same. Sorry, y real is actually y, so y values will be assigned to this function y real. I can define it directly over here as well, so no problem, whatever suits you best. So let's see and simulate this result and see if it works. Plot figure. Wait a moment, I'm not sure why it is not showing me the result. Plot t minus, let me write it in command window, plot t comma y underscore real. Let's see if it works this way. Yes, so this is our real output, and then hold on y estimate. I'm not sure why it is not plotting on the same plot. Let me see here. Let me hit grade on. Let me stop my simulation over here. So when it actually stops somewhere and I'm unable to figure it out, I get my values over here. We can see in the right hand side workspace. Okay, let me add a stop over here whenever we write keyboard. So after each iteration this should stop. Let's see, and then prompt me. What exactly is happening? Let me comment out this. For some reason, okay, same time dt t x1. Now I am running code with each step. Y real, m, n, w, all these values initialized. Sigma, okay, y hat, error, eta. For loop begins. For loop x vector, linear combination, activation, estimation, error. Then gradients are calculated. Then weights updated. For some reason, I'm not sure what is the reason behind this, that this line is going back somewhere. Okay, I figured it out. This is the mistake over here. This needs to be D. I wrote it capital. So let's run the code now without this break. And see, yeah, so we can see our figures here. Let me put a command for legend, and let me distinguish these plots from each other as well. So let me use a line width of 2, and let me use a color R, which we usually use, RGB. You may be familiar with that. Line width, I don't want to make a mistake again, 2, color blue, and let me choose line style as well. Yeah, this is what I was going to do. Thanks to MATLAB for recommending these commands to me. And let me write legends as well, so we can see what happens. So the first one is actually real, and the second one is approximated function. Okay, so let's see if we are getting our values. Okay, there is one mistake. Y real, y estimated. Now I just realized this. Here we have y hat equal to zeros of this. So I think that I made a mistake over here, and it is plotting only one result. Y estimated. So I need to move this value to another variable, just like I did up there. Yeah, I realized this. So when first iteration happens, this becomes y estimated. So for example, we get some value, let's say 10. When second iteration is performed, that 10 value is replaced again with these new updates. So we need to save this. Let's say, let me call it as y hat, which I have defined up there. Y hat is equal to y estimation. Okay, let me see if I have defined y hat over here. Yeah, so I'm storing the estimated values in the first instant, then second, third, fourth, and so on. So now let's see, I don't know what exactly is the reason of these small bugs, or I don't know what is the issue. Let me see. Yeah, we reach here, we plot this, then we plot, hold on, this should not happen. This should not happen at all. Let's see. Okay, I know I made a mistake with colors. I think I made a mistake with colors. This should be y hat for all the series, and let me remove these commands just to avoid this confusion. Let's see, once it works, then I can clean this code later on. Yeah, So we can see the approximation now. So you can see this approximated, which is a red line, and the real line is the blue one. So approximation is not really good if we look at this way. So what we can do is that we can tune our learning rate, which I set to 0.1, or I can increase the number of neurons. But before that, let me clean this code a bit. Line width, okay, 2. Let me see if it works. I don't know exactly why this was a problem. Yeah, now we can see it much better. So let me do it for this. Line width 2. So this is our result. By the way, we can also plot the error. Let's see if our error is approaching 0. So plot t comma e, but this will not work. I will tell you why. I will tell you because we have not saved e separately. We have not saved this e separately. Line width 2. So yeah, you can see we have no plot for it because I remember here I defined an array for error, right? But I did not save the value of error in this array. So we obtained ERR, which was error here. So let me save this in each instant. So I believe it will work now. There are so many bugs, or I don't know, maybe I'm making some mistakes. Perhaps figure 2 t comma, this should be error. Yeah, the easy way to find out the mistake is that you click it. When it gets highlighted, it means it is defined up there. And if I write it like this, you see, so I click it, it does not get highlighted. It means this is a new variable here. So that's why we are getting an error. So now I believe this will work. Yeah, we can see our error. It is crossing 0, but it's just fluctuating and not staying at 0. So let's do something and tune it. First thing first, let's increase the number of neurons. So we know that here the number of neurons are 3. Let's increase it to 10. Okay, so now it will perform all the neural networks but with 10 neurons. So you can see our result for error is changed, and it is much smaller. If you look at the y-axis, it's smaller than before. And let's see what is the result. Yeah, so you can see again the approximation is also changed. It has improved but not really well. Now let's choose 15 value for the number of neurons. You can see again this is much improved now. It is staying at 0. Let's see approximation. So once again we can see approximation is improving. So instead of this, let's try to change the value of tuning parameters. So let's see. Yeah, so now you can see the error is very small. It stays between 0.2 and minus 0.2. So you see here our approximation is improved even further. Let's set it to 0.3. So yeah, you can see error is changed, but now we are getting all these overshoots and ripples in our results. So instead of increasing the number of increasing the tuning parameter, let's increase neurons. So this is just a trade-off, and we can play with it and achieve our desired results. So let's see what we get here. So you can see our estimation and approximation is improving with time. We can also change this time parameter as well. approximating our neural network at 0.1 second. Let's make it 0.01 or even smaller. So this may take more time. That's why you need high performance computers for AI, but this will result better. So you see our error is very small, 0.05, and it is staying at 0, I would say. And approximation will be really good here. So you can see they are at the top of each other. So to make them clearly visible, let me change the line style of, sorry, this is the wrong, let me change the line style to set it to dashed line. So even when they are at the top of each other, we will be able to distinguish it. So this is the error, and wait, sorry, this is now the dashed line, sorry. Yeah, this is the error, and now you can see approximation is really good. So this was all about the neural networks, and you may have seen the code is not that difficult. When there are some beginners and they want to learn neural networks, they are overwhelmed with a lot of equation. We go online in Google or ChatGPT or books, we see all these equations, and even before beginning it, we get confused. But the mathematics involved in neural networks is really easy. Just to give you a recall in few minutes before I close this series of videos as well as this programming lecture, there are two steps in each neuron. First one is to do linear combination, and then we have to do activation. These are standard methods. What we have to do after that, we have to calculate estimated function. So once we calculate the estimated function, after that we have to find the error and minimize it. Then for that we have to make a loss function. So once we make this loss function, we derive these formulas. So now they will stay same for all these neural networks for me, and then I will input these formulas in the code, update the weights, and design. That will be finalized. That will be finalizing our neural network. And then to see the results, we just have to add these commands. The thing is that neural network estimation depends on two things. That number one is number of neurons. Number two is this learning parameter. But if we keep this time instances very big, for example, let me keep it 1 second. So we will have only 10 points of instances. So we will have different results. Now you will see over here. You see error. It is calculated at 0, then 1 second. You see then 2 seconds, 3 seconds. You will also see the graph is also really weird. It is plotted at each second. So what we can do is we can set this to 0.00 value, even smaller than this, right? So it will be calculated at all the small instances, and then our neural network will work this way. So you see, this is approximated function. Every time this code is operated here, this chooses some random values. So this is the command of MATLAB. Similarly, random value for output weight. So instead of manually choosing these values, I gave them random values. I can also write a matrix W with my own choice, but why not use the random values? So this is it, and I hope this series of videos helps you. This is just a beginning, and there are a lot of things involved in neural networks, but just to give you some motivation and encouragement, I hope this series helps you and you begin with neural networks. Thank you and good luck.